Everyone, I am Hanming Zhao, and my partner is Divya Eashwer. We are part of the Material Science and Characterization Lab under Dr. Starostina. Our project is the evaluation of mechanical properties of 3D printed PLA in two printing orientations and between two printers.
Divya, you on?
I realized I was muted.
Yes.
So first of all, what is 3D printing? 3D printing or additive manufacturing is an emerging technique of manufacturing for the construction of a 3D object from a CAD model with the ability to create complex designs unlike traditional manufacturing, in which products are formed or casted. Now, 3D printing works by depositing material through a layer-by-layer process to produce products from ground up. And traditional or subtractive manufacturing works with the raw material and removes excess material. Now, 3D printing, as a result of this, subtractive manufacturing ends up wasting much more material. And additive manufacturing is generally used for rapid prototyping since it degrades material properties. So we aim to characterize the difference in material properties between the additive and traditional means in this project.
Okay, so our material in question is PLA or polylactic acid. Polylactic acid is a thermoplastic polymer with the formula C3H4O2, and as a polymer, it is a very long strand of that. It is formally obtained by the condensation of lactic acid with the loss of water. Pellets are heated and then spun into 3D printing, 3D so it is then spun into filament, which is what the 3D printers use, and it is the most frequently used thermoplastic in 3D printing, with the other one being ABS. Relative to ABS, it is biodegradable and more environmentally friendly, as that is because it is derived from biomass, while ABS is made from fossil fuels. The reason why we want to characterize the mechanical and physical properties of these materials is because the properties are needed for finite element analysis, which is crucial in mechanical engineering.
So the goal of the study is to 3D print ASTM tensile test specimens in both the vertical and horizontal orientations in the Prusa and Bambu 3D printers. And we also want to injection mold ASTM tensile test specimens. And then we'd be comparing the mechanical properties between the two orientations and the two different printers. And then we'd be comparing the mechanical properties between the 3D printed tensile dog bones and injection molded parts. And then lastly, we'd be comparing our data to data already available in our literature search.
Okay, so let's talk about our sample preparation for our tensile tests and hardness tests, with this one being more about tensile tests in particular. So for our tensile test, we need a dog bone sample, which is designed according to the ASTM D638 standard, the standard for polymers. So for our traditional samples, we want a injection molded sample, which we have to injection mold with a machined aluminum block. And then we have our 3D printed samples, which are printed on a Bambu and Prusa i3MK3S printer. These are all done in-house and from the exact same PLA, albeit this is from a filament feedstock, while the other one uses pellets. The flavor of ASTM D638 we have chosen is the Type 1 sample, which is the largest size available.
So our tensile will be doing tensile testing, courtesy to Santa Clara University. And this machine measures the stress strain diagram, which yields the ultimate tensile strength, yield strength, Young's modulus, and ductility or percent elongation. And then density and dimensional accuracy measurements. And here we'd be comparing bulk pellets density and identifying the most shrinkable dimensions, if any. And then the X-ray diffraction. So already 4 samples were given to EAG for partial crystallinity characterization. And we're doing this because, according to our literature search, partial crystallinity of the feedstock polymer is one of the parameters linked for mechanical properties.
Okay, so let's talk about where we have gone with our injection molding. So we're slowly continuing to uh work on our injection mold. As you can see, that's the progress. Right now there is still a little bit of residue left over from the machine, so that's the black spots. But we do expect that with future iterations we will be able to fully produce the sample to the quality where it would be acceptable for us to test them in the tensile test machine. These are also injection molded at SCU, so thanks to SCU for helping us get that done.
And these are our 3D printed tensile test specimens. We have two sets on each 3D printer. So there's 26 specimens in total and two sets of 12, and half are horizontal samples and half are vertical samples with 3.2 millimeters and 6 millimeters thick. And all of them are printed with the same neutral EOS print filament. And then we also 3D printed 1 centimeter cubes for the density and dimensional accuracy test.
Okay, so let's talk about our dimensional accuracy and density measurements. So we printed 5 cubic centimeter cubes, and as you can see up here, these are our numbers and that's the raw data. So our methodology was to measure X, Y, and Z for each cube with 3 points on each side, and then we took the average. So then after that, we measured the mass of each cube. So our hypothesis was that the density does not match the CAD or the bulk number given from the manufacturer because of pockets of because pockets of air that are created during the 3D printing process and the effects of gravity. And the results more or less uh, helped us confirm that. So the X and Y dimensions, which are the horizontal dimensions, expanded by 0.7 and 1.01% respectively, while the Z height, which is the vertical one, was marginally lower than CAD expectation. So overall, the measured mass was also lower, so we could confirm that the actual density was quite a bit lower than what we were expecting based on the data that we had.
So these are our results for our stress strain diagrams in two different orientations on the Prusa printer. So on the left, it shows the horizontal for the horizontal specimen, and the right shows the vertical. So the horizontal one shows that it was somewhat ductile, because this is a classic stress strain diagram curve, and it breaks off around 7-8%. While in the vertical sample, it seems very brittle and it breaks off much earlier, around 2-ish to 4%. And some potential causes for the differences is that the printing layers are aligned with the tensile test direction for the horizontal print, and then the layers are orthogonal to the tensile test direction for the vertical print.
Okay, so next up, let's take a look at the stress strain diagrams for the Bambu printers. So much like the Prusa printers, the horizontal samples were more or less ductile, while the vertical prints were pretty brittle. You can see this in that the horizontal sample breaks off at about 7% elongation, while the brittle sample, which is the vertical one, breaks off at a mere 3.5% elongation. Again, this is probably the same reasons.
So this is a stress strain diagrams when comparing vertical specimens between the two printers. So the left side shows the Bambu and the right side shows the Prusa printer. So as you can see in the stress strain diagrams, they both show very similar behavior. The graphs are very similar. And however, it's slightly different in the ultimate tensile strength, like the highest point. And these potential causes for differences could be because of different print setups, the variations in printing parameters, and that Bambu is an enclosed printer while Prusa is not.
Now let's take a look at the difference in the horizontal samples. If you could return to the previous slide.
Yeah.
Okay, so you can see how the Prusa printer is still somewhat more ductile than the ones printed by the Bambu. The Prusa does have a lower, it also has a lower ultimate tensile strength. The Bambu printers consistently broke at around 5.5 to 6% strain, while the Prusa ones broke off at around 9.5% strain. Again, these will probably be caused by the differences in between the design and ultimate printing conditions in both printers.
So this is the collection of all of the data from our stress strain diagrams. And it is currently a work in progress, and we're yet to analyze it in depth. But so far, you can see that young our young moduluses are very
अरे
similar,
ज्वाइन कर लो मीटिंग
very similar between all orientations and printers. However, there are some differences for the other mechanical properties.
Okay, so let's talk about our data in comparison to our literature search. So in our literature search, we saw a average Young's modulus for PLA that is about 2.6 gigapascals. Meanwhile, in our own experiments, we had around 1.2 to 1.5 gigapascals, depending on the print orientation and the printer, uh, and the printer. And then next up, we have the yield strength, which usually is not reported too much in the literature search. Yield strength is used more for mechanical engineering applications, and since PLA isn't a very common material used in that space, most studies chose to forego this particular number. The percent elongation in literature was about 4.6%, and we experienced 2.7 to 10%, depending on the specific print. And our ultimate tensile strength was pretty similar to the literature search at 44 megapascals versus the literature's 50 megapascals, and the ultimate tensile strength for our vertical samples were likewise pretty similar.
So looking at the data and the comparisons with literature search, our data is generally agreeing with the literature search, especially in the ultimate tensile strength. And later we are going to be finalizing the stress strain data analysis and then report the findings at the expo on March 22nd. And we will be continuing to do the literature search to have a more detailed comparison between the our data and the literature search. And we will be continuing to suggest the working ideas or hypothesize why there is a difference between the print orientation and if the sample thickness might be a factor to consider. And then lastly, we realized after searching for any other projects that found the yield strength of the PLA that we are the first to report yield strength based off of whatever we have researched so far. So we'll continue to research that.
Okay, so for our future plans, one of our most important plans is to finish up the injection molding at Santa Clara universities so we can properly compare the traditional forms of manufacturing to additive manufacturing. We will also follow up on the XRD data from EAG, which we just received recently. We will then analyze that data and report later this month. Some other things that we will consider doing is taking a look at the thermal expansion coefficient and viscous elastic properties of PLA for interpretation of our dimensional accuracy data. And we will also pursue hardness tests in-house and microscopic characterization of the fractured surfaces from our tensile tests.
These are our references.
Okay, I would like to thank ASDRP, Dr. Starostina, and our parents, SCU and EAG for helping make this project possible. Does anyone in the audience have any questions?